In this video, we're going to see common gate stage of a MOSFET. This is how the circuit diagram is, where at source terminal we are applying the input and at drain terminal we are taking the output. The common one is basically the gate terminal. At gate terminal we are applying a DC voltage, and at source terminal we have a DC voltage. Let's say this is VSS, and here we have a small AC signal applied on top of the DC voltage that we have. So for DC analysis, we have VDD is equal to IDRD, as the current that flows here will be equal to ID, plus the DC output voltage V0. Obviously, the DC output voltage V0 will be equal to VDS, the voltage across the MOSFET drain to source, plus VSS. And when we look at the equation at the input, the biasing voltage VB for the MOSFET at gate is equal to VGS plus VSS. Now let's look at the small signal analysis of this circuit, in which all the DC sources will be made 0. So VDD is made 0, VB is made 0, VSS is also made 0. Hence the equivalent AC small signal circuit diagram would look like this. From this we can write VGS is equal to minus VI. If you write the loop equation here, let me take this is the drain current that is flowing through, and if you take a KVL here, we get V0 is equal to the voltage across R0, which will be ID minus GM times VGS times R0 plus the input voltage VI. Now we know what is VGS, which is equal to minus VI. Let's substitute that here. V0 is equal to R0 ID plus GM R0 times VI plus VI. Now another thing, that ID will be the same ID flowing through RD also, where we will have potential like this, but the reference output potential is opposite. Hence we write V0 is equal to minus ID RD. So let's substitute in the above equation that ID value here. Then we get equation like this, where we can write V0 over Vi, which is the voltage gain, equal to 1 plus GM R0 over 1 plus R0 over RD. This will be the voltage gain of this stage. Now let's find the transconductance of this stage. Hence we have grounded the output terminal. Now let's see what is this ISC. Obviously this current cannot be flowing through RD because the voltage across it should be 0. Hence current flowing through RD should be 0. Hence the current here should be equal to ISC flowing into the drain. Now we can take KVL in this loop, where we get voltage across R0, which will be ISC minus GMVGS times R0 plus VI should be equal to 0. And we know other equation that VGS should be equal to minus VI. This we get by taking loop equation here. Now let's substitute this VGS value here and find what is the ratio of ISC to VI. We get ISC over VI is equal to minus 1 plus GM R0 over R0. Now let's look at the output resistance of this stage. Now obviously in this case, as we make Vn equal to 0, VGS here is 0, hence the current that flows through the MOSFET will also be 0. Hence Ix that we talk about here when we apply Vx would flow through the resistance which is in parallel, R0 in parallel with Rd. Hence obviously Vx by Ix, which is the output resistance, will be equal to R0 in parallel with capital Rd. Hence obviously by knowing transconductance and output resistance, we can verify the voltage gain that we got, which is minus capital GM times R out should be equal to minus of minus plus, which is 1 plus GM R0 over R0 times R0 in parallel with RT. Now in this case we cannot say input resistance is actually infinity. Now because we are applying the signal at source terminal. So we have to find out what is input resistance. Here this is VGS. Obviously VGS is equal to minus Vin, and voltage at this node would be 0, hence current flowing through RD will be 0. And we have a current flowing here which is GMVGS, and let's take this is the current that is flowing through, which is I in. We can say the amount of current flowing through R0 will be equal to GMVGS plus I in. So hence the voltage across R0, if you take the KVL here, we get minus V in plus voltage across R0 is equal to 0. So we can write V in is equal to voltage across R0, which is R0 times GMVGS plus I in. And we know what is VGS value here. Let's substitute. Then we get equation like this. And then we can segregate and write V in over I in, which is equal to R0 over 1 plus GM R0, which is in fact is equal to 1 over GM in parallel with R0. We have seen this resistance expression for a MOSFET in diode connection. If you observe carefully here that current flowing through RD is 0, which means we don't even consider that, and gate and drain terminals are grounded. Hence here the MOS transistor is actually in a diode connected fashion. Hence obviously by looking at it we could have written this expression straight away. So in common gate stage the input resistance is going to be less. If you look at the overall analysis we did for common gate stage, the gain doesn't have a minus sign, which means the output voltage is not going to have a 180-degree phase shift compared to input. And coming to the input resistance, for common drain and common source stage, we always had input resistance very high, and we said it's infinite because we see gate to source terminals at the input. But in this case, the input resistance is finite as we are driving the input signal through the source terminal. Thank you for watching. See you in the next video.